But yes. Hello, everybody. We will get started in just a second. This is the review session for 61B on sorting. We had review sessions yesterday and the day before as well, and those are or will be soon be posted on Ed, the recordings for those. This will also be recorded, so please don't have your cameras on unless you're comfortable with your face possibly showing up in the recording. Please feel free to ask questions both in the chat or out loud when we ask for questions. It's even better if you ask them out loud because people watching the recordings cannot see the chat. So if possible, we will really encourage you guys to ask questions out loud. But other than that, I'm going to turn it over to Sean and Nishant because they're going to be presenting today. And you guys can go ahead and get started.
Sure. Does everyone see this? Okay, I'll assume so. Okay, yes. Awesome. All right, so today we're going to talk about sorting. And we're basically going to go through all the comparison sorts, and then we have a couple of radix sorts to go through. Slides. Yeah, I think someone will put the link to the slides. Yeah, so anyway, without further ado, we'll just get started with selection sort. So selection sort is like one of the most basic sorts. You probably would think of selection sort or use selection sort when you're sorting something by hand. And same with insertion sort. So let's just step into what selection sort does. So selection sort is an unstable sort that takes O of n squared time. And all we're doing in selection sort is we're going to scan the current array, find the minimum element, and then swap it with the first element in the unsorted section. And what's going to happen is on the left side of our array, we're going to start having like a sorted section. And that's like something that we're going to maintain the whole time. And by the end of this algorithm, our entire array will be sorted, or there will be like no unsorted section left. So let's just take a look at like the first few steps of the algorithm. And it's fairly like mechanical in this process. So I'm not going to like step through the entire thing, but we're going to search first, and we find the first occurrence of our minimum element, which is this one, and we swap it with the first element. We do it again, and we see 1b, swap it with the first element. And now we scan again, and we find 2. And this is why selection sort is unstable, because notice that this 2 sub a element, it occurred initially in the beginning of our, like all the way over here as the first element. After we moved, so after we moved it over, notice that now it's in the sorted section, and after we complete this step, this sorted section is no longer stable because our original ordering or pairing of our elements is no longer, like that no longer exists. So we would continue this whole process. So we continue this whole process until the entire list is sorted. So it's fairly like simple in its total procedure because we just keep scanning, we keep swapping, and yeah, that's about it. So now let's talk about the runtime and also space complexity. So the runtime of this algorithm is theta n squared because if we think about what we were doing here, every single time or every single step of this algorithm, we were scanning the entire list, searching for the minimum and making a swap. So when we think about that, no matter what our list is, even if we're already sorted, we swap with its neighbor or swap with the item at the beginning of the list. Okay, yeah, so this is like, I think there's like something that I was also confused with before when I took the course, and it's between selection sort and insertion sort. So with selection sort, we're finding the minimum, we're always swapping with the item at the beginning of the list. I'll talk about insertion sort like very soon, but insertion sort is where we swap with the neighbor until we've reached a point where we don't want to swap anymore. But I'll discuss that very soon. Okay, yeah, so back to say like why these are the same. Selection sort will go through the same process even if everything is sorted already. So we can imagine for some sorting algorithms that an already sorted list will only be like n or O of n time, because we just need to go and see through the list. And if it's sorted, maybe we don't do any operations. But in this case, we'll always have to search, do a swap. And in this case, we're not swapping anything, but we're still searching through the 5 elements, then 4, then 3, then 2, then 1. And we should know from asymptotics that this sort of relationship, this boils down to theta n squared. But our space complexity is still theta 1, because it's constant and we're not actually using any extra arrays. Okay, cool. So, and it's not stable, right? So now let's move on to insertion sort, which is sometimes confused with selection sort, but it's also a sort that takes quadratic time, but this time it's a stable sort. So essentially our algorithm, and this is going to be for a non-in-place insertion sort, is to look through the array, and we take an element in the array that hasn't been sorted yet. We add it to the correct spot in the empty array, and we repeat until the entire array is sorted. So here we take the first element, we add it to our array, then we take the next element, we perform a comparison with what is in our empty array or the new array that we initialized, and we place it in its place. And we keep going. So here we'll have to make 2 comparisons, and we notice that 3 is in between these 2, and we slot it in. Okay, so after we slot that in, we're just going to keep going through this. And because of the ordering that we're scanning through our original array, this is going to be stable because we're not going to change like our current ordering of these 2 elements, and we're only going to keep it after a certain element that we see. So like after we place 1A, when we go and find 1B and we say, oh, okay, this is, we compare it here and we're like, oh, okay, so this goes, this is the same, like they're equal. We're just going to add it like right in between, so it's still stable. Okay, so this is like our not in place insertion sort, but we can totally do this in place. And this is going to take up less space, because in some cases, we don't want to use like a whole nother data and space. Yeah, okay, so what we're going to do is essentially we're going to take the first element in the array that hasn't been sorted yet, and this was referred to in the chat, that after we take this element, we keep performing comparisons with the items to the neighbors to the left of it until we reach an item that is smaller than the current item or equal to the current item. So we've skipped a bunch of steps here, but now we've reached a point where we have 1A, 2A, 2B, 3, and 5, and now we have this like unsorted section. We take our first element and we keep swapping. So we notice that it's less than 5, we swap, less than 3, we swapped, less than 2, twice. And now in this situation, we notice that we're still equal, we're less than or equal to whatever element, or greater than or equal to whatever element is to the left of us, so we don't need to swap anymore. And then with 6, we would have compared for the first time and noticed that it's in place and we have a sorted array. Okay, so if we assume that swapping was like just a constant time operation, then we actually, what we're distinguishing from selection sort is that selection sort was always quadratic time, but in certain situations, insertion sort is better. So our best case time complexity is theta n, because what we'd really be doing for an in-place insertion sort on this already sorted list is checking to see if it's sorted. Because as we go through and we find the element that hasn't been sorted yet, and for 1, it doesn't matter, but for 2, we're performing 1 comparison here, 3, another comparison, 4, another comparison, and 5, another comparison. So we're only performing n comparisons, which is why we have theta n best case time complexity. So our worst case time complexity is still scanning through the entire list, but we're going to have to perform a lot more swaps. And this is why we're going to have a quadratic time for a worst case. Space complexity, again, if we do the in-place sort, it will be constant time. If not, we'll have to use linear time, or sorry, like constant space, and otherwise it'll be linear space. And this is a stable sort, as we mentioned before. Okay, So let's just do a quick, which cases would an insertion sort be better for than other sorts for? So generally insertion sort, because we have to do like fewer swaps for insertion sort. We want to use insertion sort for cases where we have like less than 15 elements, and that this has been proven empirically. But those are situations where we use insertion sort over some of our faster sorts, which we'll get into later, like quick sort and merge sort, which are proven to be very fast, but they're not as fast for insertion sort because of some overhead. But yeah, we have a quick little check-in question, and just take a few, like 30 seconds to think about, take a few seconds to think about which of these two, between selection sort and insertion sort on a completely reverse array, which one will take fewer swaps to finish. So we're not concerned about runtime necessarily, but we're just concerned about how many swaps we're going to take. Okay, 30 seconds are up. Does anyone have any? Okay, everyone is saying, or a bunch of people are saying selection sort. Does anyone want to say why that's the case?
For example, when one swaps, the 6 just ends up in the correct place and like so on. So like when it gets like 6, it doesn't actually have to swap.
Yeah. So that's right. And what Patrick said in the chat is also correct. So selection sort is performing fewer swaps, but insertion sort we'd have to do, in this case, we'd have to swap every single time. We'd have to keep swapping with our left neighbor, and we'd actually have n-squared swaps. So we have fewer swaps in selection sort. Okay, cool. Let's move on to heap sort. Okay, so heap sort is an unstable sort, and it takes O of n log n time. And what we're doing for heap sort is we're taking advantage of the heap property, and we're going to use a max heap. So essentially what we're doing is we're tossing all of our elements in our current array into a max heap. And after we do that, we heapify the unsorted portion, and then we pop off the largest element by swapping it with the last element in the unsorted portion, and we repeat until the entire array is sorted. So like the details of like heapifying and such, I'll assume that we know that already, but we can now just go through how this would work on this current unsorted array. Okay, so first we have this array, we put it into our heap, and now we heapify all the elements. So what that means is we're just maintaining the heap property, so we have a complete heap, and that each node is like greater than or equal to each of its children. So we now have this in our heap property, and we'll pop off our largest element and swap it with the current last element. Because we're doing a max heap, the largest element is always the largest element that we have, and we have to put it at the end of our array. So we pop off 7, swap it with 3, and now we have to heapify that heap again, which gives us this. And we continue by swapping, and we do it on each unsorted array, and we notice that this right side is now sorted. So as you continue, you keep going, and notice that because we're heapifying, there's kind of an arbitrary nature to which element is going to become our root. So after we sink, or after we like swim every single element, or sink every element when we're heapifying, there may or may not be the same element that's going to the root. So in this case, 2 sub a actually was in the root, and after we popped it off, this sort was no longer stable. So that's why like heap sort isn't stable. but we would keep going. And finally, at the end of this, when we have no longer, when our heap is like size 0, our entire remaining array is sorted. Okay, so our best case for heap sort is theta n. And that's like in a situation where, let's say we had all the same elements. After we throw it into our heap and we keep popping off, we're not really, we're only performing a few swaps, and that's theta n. But our worst case is theta n log n, because each time that we're heapifying, this is going to cost us log n. Like our heapify operations are log n. The first time we created our like put everything into our max heap, that cost us n log n. And then because we have n elements, it works out to be theta n log n. And we're also able to do this in place because we're basically making our max heap the array that we already had passed in. And we saw that this was not stable. Okay, so we just have a quick check-in question. Supposing that we're sorting an array of 8 integers using heap sort, and this is like with the max heap sort, and we just finished a few heapify operations, just like we showed on the previous slides. And now we have this array, 16, 14, 15, 10, 12, 27, and 28. So the question is, how many heapify operations have been performed on the root of the heap? So I'll give you guys another 30 seconds to think about that. All right, it's been 30 seconds. What do you guys think is the answer? Okay, yeah, looks like 2 is the consensus pick for this question. Does anyone have an explanation for why you picked 2? Yeah, you can see 2 elements have been popped off. Right, so if we look, we know that we're doing heap sort, and we know that whatever unsorted array has to maintain the heap property. We see at the root, the original array had 27 and 28 at the end, would it still take 2 heap operations? Yes, so I'll just finish explaining and then I'll answer your question. So yeah, so if we know the unsorted array maintains the heap property, and we see at the root that this is 16, which means that the elements greater than 16 would have been popped off. And 27 and 28 are the ones popped off. So like the last 2 elements are also the max 2 elements. Yeah, so to answer your obvious question, he says if the original array had 27 and 28 at the end, just like it is here, would it still take 2 heap operations? And I think Patrick answered it because if we go back like just to the steps of our heap sort, we heapify all the elements of the unsorted portion of the array into a max heap. And once we heapified, once we heapified this array, yeah, 28 would definitely be at the top, and also 27. And we'd still have to pop that off. We'd have to pop 28 off and then reheapify. Oh yeah, we're not counting the initial heapify. So sorry. Yeah, I guess that was unclear. So 2 on the root. So it was on the root of the heap. Yeah. Okay, does anyone have any questions about heap sort, insertion sort, or selection sort before I get into merge sort? Okay, does the heapify operation mean sync/swim? Yeah, so well, heapifying is to make sure that our heap is maintaining the heap property. And essentially, when we heapify some heap, we're going to sync every single node in, I think it's level order. So in level order, we're going to sync every node. And this heapifies the heap. So I'm not sure. Yeah. So the details of that would be, I'm not going to go over right now, but that's basically what heapify is doing. Okay. The list is sorted backwards from the beginning. Yeah. List is sorted backwards. Let me think about that question. But I'll start. Can you remove max? Yeah, so removing max, if that's like an operation that our heap has, then remove max would also heapify the whole heap every cycle. So we're kind of in our steps, we're just assuming that we swap, and then our heap has kind of changed. Because the difference is that if we go back to like maybe this, like this stuff here isn't part of our heap. So after we swap with the last element in the unsorted position, and we swap this part, these things aren't in the heap anymore. So we're adding something like that wasn't in the heap to the heap, but yeah, I think remove max would also heapify at the same time. So in terms of runtime considerations, it would be the same situation. Okay, I'm going to move on to merge sort. So merge sort is now a stable sort that takes O of n log n time. And what we're doing, and it's a recursive algorithm. So essentially what we're doing is we're splitting the array into two even halves. And if we don't have an even number of elements in our array, we're just going to arbitrarily split like 4 or 3, 3 or 4. That specific implementation is not as important. And you're going to recursively perform merge sort on each half of our array. And then finally, you're going to merge the two halves by zippering them together. So there's like a lot of steps here because if we're doing it recursively, but what we're going to show right now is just having split this array, we perform merge sort on each half, and this would actually be a recursive algorithm. So we'd actually continue splitting until we're left with one element in each of our little arrays, and in this case, two. No, one element in each of our arrays, and then after we zipper them together, we're assuming that now we're left with like these two sorted halves. So notice that each of our halves are sorted because we perform merge sort on each of the halves. And then finally, we're left with like, this is like basically the final step before we're sorted. And what we're going to do is we're going to compare the first element from each of our two sorted halves. And whichever one is smaller, we're going to put it into our final output array and move over the pointer. So in this case, one was smaller, we put it in, moved our pointer over. One is smaller again, we put it in, move our pointer over. Now 2, 2, and 3 are all smaller. So we keep putting these in. And finally, we have 7 and 6. 6 is smaller. Now the right side of this, or the right list, is completely empty. So we slot 7 in. So this is a process that has happened after we split all of our entire array into like one element pieces. We've zippered them together in this very process, just merging sorted or two sorted arrays again and again and again until we've reached a final sorted array. So merge sort in the best and worst case is n log n time. So if we draw out the recursive tree as you have had practice with in asymptotics, you're going to have log n depth for your tree, and then we're doing n work at each level. So it's a total n log n time, and this doesn't change no matter what our array is. we're still going to spend like n log n time doing merge sort. And finally, the space complexity of merge sort is theta n, because we have to like essentially we have to add stuff to a new array each time. I think there's basically no one knows how to do merge sort in n log n time without, or like not using extra space. And the sort is stable. So it says if we broke ties by using, someone asked if we broke ties by using the right pointer's element, merge sort wouldn't be stable anymore. Yeah, so if we assume that maybe we sent 2b over to this side, and it would slot in here, and it was instead 2a, yeah, so anyway, if we, let's just say that we had like 2b over here on this side, it would, if we use the right pointer and we noticed that they're the same and we broke the ties, yeah, if we use the right pointer, then 2b would essentially, it would move ahead of 2a. And that's why we would actually want to break ties using the left side. Okay, why is merge sort space complexity theta n? Yeah, so essentially what we're doing at each of these steps is we have to keep copying each element into a new array. So like when we started here, we're splitting all the elements into their pieces. And as we're like zippering them together, we have to create, so like, so before we did this merging, this is like a brand new array that we have to add stuff into. And we're doing this at each level. So that's why it's theta n. Does that answer your question? Okay, cool. All right. Just one more check-in question is if we wanted to sort this list, 20, 47, 15, 8, 9, 4, 40, 30, what is the order of the elements after one merge of merge sort? Like one merge operation. Okay. People are saying C. Why do you think so? Or why do you guys choose C? Yeah, Brian.
You would sort the left and right halves separately. So the first four and then the second four, sort them before they're merged together.
Okay. Yeah. So I guess this is a little bit tricky. It might just be like a little wording issue, but the answer is actually D, because we're saying after one merge of merge sort. And what we're doing is we're splitting everything down into, like, the way the algorithm works is that we're splitting everything down to single elements. And now we're starting to merge everything back up to the top, right? So after we split this up into 20, 47, and like little lists of 20, 47, 15, 8, 9, 4, 40, and 30, that merge would be just 20, 47 merged together, 8, 15 merged together, 4, 9 merged together, and 30 and 40 merged together. So we're just making sure that these, after like one merge, that these little lists now of size n over 4 are merged together. And then the next step would be to merge together this list and this list and this list and this list. So I don't know, maybe it was a little unclear with the question, but that's essentially what the answer is. Okay, does anyone have any questions about the last few sorts? Yeah, so this would represent like the bottommost level of merge, exactly. Okay. Yeah, so with that, if you have any other questions, feel free to put it in the chat and I'll answer it. But now Sean will cover quicksort and some radix sorts.
Okay. Yeah. Okay, so I'll be covering quicksorts and radix sorts. So the first part of quicksort is that in general, we choose some kind of pivot for our algorithm. So the point of the pivot is to partition the array that we're working with into two parts. And the pivot serves as like a point for where you have your elements that will be less than the pivot and the elements that are greater than the pivot. So upon each iteration of quicksort, we rearrange the elements in the array to make sure that the elements that are less than the pivot will be to the left of it, and the elements to the right will be to the right of the pivot. And because of this scheme, after each iteration of quicksort for every pivot, the pivot will end up in the final correct position for where it should be in the final sorted array. And then we'll keep repeating this scheme where we pick the pivot and then create these left and right partitions until the entire list is sorted. And when your partitions are of size 1, usually that's when you know that you have created a small enough partition to know that it's in its correct sorted position. And we'll go through some more examples of these to make those more clear. So for an example of a pivot, let's say we have this arbitrary unsorted list. And for the sake of example, let's just say that the pivot is 4. So in our final output, or after this iteration, we should see that the elements that are smaller than the pivot, namely 3, 0, and 1, should end up to the left, and 7, 9, and 5 will end up to the right. So we can see that here, the pivot has moved to the middle, and the elements that are smaller have moved to the left, and the elements that are larger have moved to the right. So again, if after an iteration of quicksort with a pivot, the pivot's positioning will be in the correct position in the final sorted array. So if we were to sort this whole array into its correct sort based on the number of values, then we see that 4 lines up with the same position in the final sorted array. Okay. The way you choose the pivot is really important for the runtime of quicksort. It can range from n log n to n squared based on your selection. And there's a lot of different ways we can choose our pivot. So one common one you might see on exams is just always choose the left pivot, which is kind of just a convenient thing to do just for saying you're going to pick the leftmost one. The most efficient one is choosing the median in some way. If you can find the median quickly enough, then you can guarantee that your partitions will evenly split your array into 2 even halves. And this will result in the best case runtime of n log n. You could technically randomly select your pivot, so just pick any random value in your array. And there are many other partition schemes, but these are just a few examples. So in terms of partitioning schemes, there are 2 main ones, 3scan and Hoare's. But Hoare's is the more common one because it's more efficient and it has lower space complexity because it's in place. So let's walk through the procedure for how we'll do this. So the first thing you'll do is select your pivot point. So again, this can be like your leftmost element, median, etc. And then you will initialize a left and a right pointer to the left and right ends of your array. And you will not include the pivot when doing this initialization. The left pointer will like values that are smaller than the pivot. The right one will like values that are larger than the pivot. And both will dislike values that are equal to the pivot. And then you'll perform this walking process where the pointers will move towards each other and you'll stop moving them once they reach a value they dislike. Once they've both stopped, you will swap the values that they are currently pointing to and then move both pointers forward by 1. and then you'll repeat steps 3 and 4 until the pointers have crossed. And then for the final step, you will swap the right pointer with the pivot. So let's walk through an example of Hoare's partitioning. So again, for simplicity, we're going to choose the leftmost element as our pivot. And we've highlighted the values that are less than the pivot and the ones that are larger to make it clear as to which one the left and the right pointers will like and dislike. So we'll start again by initializing the right pointers at the left and right ends of the array respectively. And remember to exclude the pivot from this pointer initialization. So because we selected 10, the leftmost element as our pivot, now we have 3 for the left pointer and 6 for the right one. Remember that the left one likes values that are smaller than the pivot, so the yellow ones, and the right one likes the values that are larger than the pivot, so the blue ones. So the left pointer dislikes the value 3 because it is less than the pivot, so it walks 1 value towards the right pointer, and it also, it likes the value 3 because it is less than the pivot, so it moves 1 value forward, and it stops at 15 because 15 is larger than the pivot, which it dislikes. The right pointer will immediately stop on 6 because 6 is smaller than the pivot, so it dislikes that value and it does not walk at all. Now both of our pointers have stopped, so we will swap the values they are pointing to. So the 6 and the 15 will swap places and we'll move both our pointers forward by 1. And then we continue to the next iteration. So the left pointer likes both 1 and 2 because they're less than the pivot 10, so they continue walking. And then it hits the value 10, which is equal to the pivot, so it stops. Now the right pointer will move and stop at 10 as well because it likes the values 20 and 17, but dislikes 10. And now the left and right pointer should swap values, but because the value they're pointing to is the same, no swap will occur, and we'll just move both pointers forward by 1, like this. And finally, because now we're done walking, we'll swap the right pointer with the pivot. And this is our new partitioning scheme. So now you can see that the old pivot ends up in its correct place in the sorted array. And we have this left partition and the right partition. And the left partition will be the yellow blocks and the right partition will be the blue ones. And now we can start our next iteration of quicksort, where we'll initialize again the leftmost element as the pivot for the left partition and the left one for the right partition as well. So 2 will be the new pivot for our left half and 17 will be the new pivot for our right half. And you'll recursively kind of call these until your quicksort is finished. Okay, so for a summary of quicksort, the best case runtime is theta n log n. And this is when you have a good pivot selection. So something that splits your array into good halves. So, and the worst case is theta n squared. So for an example of when the worst case runtime occurs, let's take a look at this example to the right. So let's say we pick the leftmost element as the pivot. Then if we selected 1 as the pivot, then when we partition the array, everything will end up in the right partition because all of the values are larger than 1. And then next time we partition, 2 will be the next pivot. And the only partition that will be created is 3, 4, and 5, which are all larger than 2. And this process will kind of continue with 3 being the next pivot and then 4 and then 5 until we're done. And as you can kind of see, because the partitions being created are of size 4, 3, 2, and 1, you kind of end up with that asymptotic runtime scheme where you have like 1 plus 2 plus 3 plus 4 plus 5. And that will result in a theta n squared runtime. So there's a question in the chat. What is the advantage for using this sort? So quicksort is regarded as the fastest comparison sort technically, empirically, as long as your pivot selection is usually good. So Java, for example, for integers, characters, longs, and those kind of primitive data types, it will use quicksort because it's the fastest. As we will talk about a little bit later, quicksort is not guaranteed to be stable depending on the partitioning scheme you use. And Hoare's, which is one of the faster ones, is not stable. So for any sorting that requires a stable sort, for example, if you're sorting objects or something, we generally use merge sort, which is another pretty fast comparison sort. which is stable instead. Does that answer your question? Yeah, so yeah, for the log n space requirement, so you can kind of see in Quicksort, you might, in the Hoare's partitioning scheme at least, it was an in-place partitioning scheme. So you'll be like, no additional arrays were allocated, and why is there a space complexity of log n? And this comes from the fact that we have to create these recursive calls that are storing the information about which one's in the left and the right partition, and this takes up space in itself. And although it's not like a direct array creation, there's space in that recursive call. Could you really quickly explain the stable versus unstable sort? Yeah, sure. So let's go back to maybe one of the earlier examples. So stable and unstable is, it applies to elements that have equal value and how they started in the array and what positions they end up when they finish. So for example, in the selection sort array, we have 2 number 2s and 2 number 1s. And the 2 number 1s are labeled with A and B as to signify that the 1A came first in the original array and 1B came second in the original array. And the same applies for the 2A and the 2B. So as we can see, as Nishant explained earlier with how selection sort works, in the final sorted array, the 1A will stay in front of the 1B, which is stable, but the 2B ends up in front of the 2A. And because 2B ends up in front of 2A, this is considered an unstable sort. For it to have been stable, all the elements with the A subscripts should have ended up in front of the ones with the B subscript. And that kind of determines whether a sort is stable or unstable. Is 3-scan empirically faster than merge sort? I believe 3-scan is like still fast, faster than merge sort empirically because it's quick sort as long as your pivot is good. But 3-scan is not as space efficient as Hoare's partitioning because you have to create a new array in order to split the elements up. But the advantage of 3-scan over Hoare's partitioning is that it is stable. So for Hoare's partitioning, we would repeat the process many times, just like 3-scan, because after one iteration, it wasn't completely sorted yet. Yes, you would have to recursively do Hoare's partitioning again on the partition tabs. Can you explain one more time why the space complexity is log n? Yeah. So even though like we don't, let me find it again. Even though we don't allocate a new array and it's technically an in-place sort, you have to create these recursive calls that are storing which one's the left partition and which one is the right partition, right? So you're going to end up having like, assuming your pivot is good, you'll have like log n levels of recursive calls. And those are what's taking up the runtime space for why the space complexity of quicksort is O of log n. But there's no actual array space being allocated. If we use 3-scan on an array of all duplicates, would it just take O of n time? Yeah, I think so, because you would just like scan through and say they're all the same and no partitions are actually created. Yeah, space complexity is worst case theta n because you would have n recursive calls. I feel like for quicksort, we don't do the same like duplicates thing. Let me think. I'll get back to you on that one, but I think, yeah, that's what you say for heap sort, but I just never heard anyone say that the best case runtime for quicksort is theta n. Yeah.
I believe the best case runtime for quicksort, no matter what, is theta log n log n. And the reason for that is similar to the reason why the best time runtime for merge sort is always n log n. And that is that even if you're in the best possible situation and you have to look at the minimal number of items on each level, there are still there's still going to be log n levels, and you have to look at every item at least once per level, if that makes sense. So if you draw out an ideal scenario, you're still going to have that situation of having to like make sure that everything is ideal, right? Even if you are cutting everything in half perfectly and stuff. And why is it space complexity log n? Does it say log n? It should be n, I believe. Oh no, no, sorry, it's yeah, one. Wikipedia says the best case of quicksort is theta n. That's okay. Oh, okay. I understand what the confusion here is. So the best case of quicksort is theta n if you are using 3-scan as your partitioning method. Because when you use 3-scan, if you recall from lecture, what you'll have is you'll scan once for everything less than your pivot. You'll scan once for everything equal to your pivot, and you'll scan once for everything greater than your pivot. And you only recurse on things that are less than or greater than your pivot. However, I think in this case, you were just only referring to Hoare's partitioning since that's what's more practically used, just because in most cases, 3-scan isn't super fast and it isn't in place. So I think, yeah, you're right. It is theta n if you're using 3-scan, but for the most part, people use Hoare's partitioning, and that's what we're referring to in this runtime analysis.
Okay, are there any other questions about quicksort before we move on to the checkoff? Okay, let's move on to the quick quiz then. So let's suppose we did the first partitioning of an array using quicksort, and it's over here to the right. And which of the following multiple choice options is true? I'll give you guys 30 seconds to think about this one, and then we can go over it. Does anyone want to take a stab at this question? Yeah, I'm seeing A's in either, and that is correct. So this is because if we took the final sorted array, it would be 1, 2, 5, 7, 9, 10, 11, and 12. So because 7 and 9 are both in the correct place for where they would be in the final sorted array, both of them have the possibility of the pivot, and all the values to the left of 7 are smaller than 7, all the values to the right are larger, and the same thing applies to 9 as well. Okay. Now we're going to be moving on to the counting sorts and the radix sorts. So as a recap of counting sorts, we use counting sorts when all keys are unique and known. So instead of doing these comparisons, where comparison sorts are locked to a omega n log n runtime for their worst case, counting sort may offer us a different way to perform a faster sort. So instead of comparing, we can just count to sort instead. So if we have a unique deck of cards and we want to sort them by suit, So everything is either a club, a heart, a diamond, or a spade. And let's say that clubs are less than spades or less than hearts and less than diamonds. We can perform a faster sort than potentially one of the comparison sorts. So the way you would do this is you count each of them individually. So there are 4 clubs, 5 spades, 7 hearts, and 3 diamonds. So because you know that all the clubs are the same, all the spades are the same, all the hearts are the same, and all the diamonds are the same, instead of comparing and moving them and swapping them and stuff like that, you can just put 4 clubs down in the beginning of the array, followed by 5 spades, followed by 7 hearts, and then followed by 3 diamonds. And that will result in a sorted array. So we can apply these ideas in radix sorts with LSD and MSD. So usually you would apply these when you have some kind of fixed character set, like numbers, digits, like you know ones are the same as 2s, 3s, 4s, etc. Or characters and strings, like A comes before B comes before C. So for LSD, which stands for least significant digit, we run counting sort independently, starting from the rightmost digit, which is considered the least significant, to the leftmost, which is considered the most significant. And if we have empty spaces in between the characters, we consider those to have less value than all the other characters. So for example, 1 has a 0 in front of it technically as the digit before it, whereas 11 will have a 1 digit before that. So 1 will come before 11. And yeah, so in this example, if we have 12, 145, and 9, you would put these like blank spaces that have less value than any other element in your character array. So let's run an LSD example on the following array. So first, we'll put them all in this column-wise fashion so it's easier to compare the digits with each other. Note that we right align so that the elements without a 100th place digit or a 10th place digit just kind of have that empty character, which will have less value than all of the other ones. The answer to the quicksort quiz was A. And so continuing off of this, now we're going to sort based on the rightmost digit. So we want all the 1s to come before the 2s and then the 3s, etc. So we sort by the rightmost digit, and you can see that they're all now in order. Note that it was, yeah, and then we move on. So now we're going to sort based on this tenths column. So we see that now the small empty character comes first, and then we have all the tenths digits sorted. Note that it has to be, oh, sorry, I think there's an error in that. This 831 was supposed to be a 731. Sorry. Yeah, and then now you sort by the 10th digit, and then you'd sort by the hundredths one last. And then you have to use a stable sorting scheme when you move from one column to the next one, because if you sorted based on the left column and then that one was sorted correctly, then you want to maintain that order when moving on to the next column. And we'll see an example of that later as well. And then you move on to the hundredths column. Why don't we sort by most significant first? So that's actually a different sort entirely. There's least significant digit and most significant digits. They're 2 different ones. Least goes from right to left and most goes from left to right. And yeah, finally we sort by the hundredths column, and now we have our fully sorted array. The runtime of, aka MSD. The runtime of LSD is theta WN plus WR, where N is the number of keys, so the number of elements that we're sorting. R is the size of the alphabet. So in the case of the numbers, the size of the alphabet is 10 because we have 0 to 9. And then W is the width of the longest key. So for example here, W would be 3 because the longest number is 3 digits long. And you perform, because you go by digit, that is included in the runtime as well. So the final runtime will be WN. So you sort by the number of keys for each digit, and plus WR, which is iterating through, going through each digit. So for example, if we go back to the cards example, you would have to go through each element, like how many ones were there, how many twos were there, how many threes were there, how many fours were there, and you have to put that many down. So you have to iterate through the size of the alphabet as well. And the space requirement is n plus r because you have to store a certain number of keys for your new array. And you need to store a dictionary which will have the counts for each element in your alphabet. And that's where the two individual components of n plus r come from for the size constraint. Okay, so like the chat mentioned, there is an MSD sort as well, which goes from the left to the right. And the process for most significant digit is similar to LSD, except we go from the leftmost digit to the rightmost digit. And the pivotal difference is that after sorting by one digit, you have to split up all the components by their keys into their own subproblems, otherwise the sort will fail. And once a subproblem only has one component, we do not have to traverse any more digits for it. So for example, if we start from the left to the right, and let's say we had 115, 152, and 213, if we sort by the leftmost column first and then sort by the right one without doing the splitting, the 213 will come before the 152 in the next step, which is wrong, even though, so basically it's not keeping track of the information it learned from the last iteration of the sort and not applying it to the current step, which is causing this error. And if you look at the final step, you just sort again by the ones column, then you'll end up with a completely unsorted array. Okay, so let's run the example on the same one we did for LSD. So you can see again, we sort by the leftmost column and have all of our values. So we're gonna split by the keys. So the ones that started with 1 are gonna be in their own subproblem, the 2 will be in its own subproblem, the 5s in its own, the 7s in their own, and the 8 in its own. So we split it like this. And because the 213 and the 831 are in their own parts now, they are no longer, you no longer have to perform any operations on them. So you know they are completely sorted. And now we just go on to the individual subproblems after that. So now we sort by the tens column for the rest of them. So the 1s before the 5, 2 before 3, and so on and so forth. And then you split again. So again, now because the 1 and the 5 are different, those will be splitted into their own subproblems. The 2 and the 3 are different, those will be split into their own subproblems. And here, because the 3s are the same, we have one more subproblem to finish in our final iteration, which we do over here. And once we split those, we know that everything is completely sorted at the end. Okay. For the runtime of MSD, the best case is n plus r. So this would happen when we only look at the leftmost digit and the sort is complete. So for example, if we had 1, 2, 3, 2, 2, 3, 3, 2, 3, 4, 2, 3, after you split the first one, they'll all be split into their own subproblems because the first digit was different all for them. So you don't even have to look at the remaining digits. You know that 123 is bigger than 223, is bigger than 323, it's bigger than 423. The worst case would be you have to look at every character for every digit. So if only the last digit was different for all of them, so like it was like 1, 1, 2, 1, 1, 1, 1, 1, 3, 1, 1, 4, you couldn't split it into any subproblems and finish any of them early, and you would have to go from the beginning to the end. So MSD, yeah, so on average, MSD would be empirically faster than LSD because you have the chance to terminate your sorting early because you split it into problems, and you might not have to iterate through all the digits. And you can kind of see that the worst, the runtime for LSD, you'll always have to go from the right to the left no matter what, but MSD, you have that chance to terminate early. The space requirement is n plus WR, so why would you ever use LSD over MSD? I can't really think of an example where you might want to use LSD over MSD. I think for the sake of this, we kind of just wanted to show you that both sorts exist and why the optimization of MSD might result in slightly better runtimes. Yeah, so the space requirement for MSD is n plus WR. You need that a little bit extra space to when you split into subproblems. So yeah, so MSD can terminate early sometimes because you'll split it into subproblems after you sort by a specific digit. So again, in this example with the 1, 2, 3, 2, 2, 3, 3, 2, 3, 4, 2, 3, because you'll split it into the by the 1s, the 2s, the 3s, and the 4s, you'll split those off into individual subproblems on their own parts. And because they only have one element in their subpart, you know that you're done with it. Yeah. So to explain the space requirement, again, you need n space for the number of keys when you create your final array with all the elements. The WR is because you have to split it to subproblems. You have to split into subproblems depending on the width of your longest key. And this can go up to the size of your alphabet because as you can see, we split in depending on the alphabet that we split on. So you can have a subproblem for 1, for 2, for 3, for 4, for 5, for 6, for 7, for 8, for 9, and for 0. And that's the size of the alphabet. So you might create that many additional arrays for your subparts. Are there any other questions? Okay. So for our final check-in, which sorting algorithm would be the most efficient for sorting strings consisting of ASCII characters? So ASCII characters is like everything from A to Z, 1s and 0s, and it also has some specific numbers for like apostrophes and stuff like that. But everything is like a character in, everything can be defined as some kind of character. And we're looking at efficiency in terms of time efficiency. We don't care about space efficiency. So we're getting some answers in the chat. There's a C, some A's, and some B's. So the correct answer here is A. It would be counting sort, because ASCII characters, it's a defined alphabet that ranges from a specific number. So you can just count the number of each character you have, and then use those to output your final sorted array. It wouldn't be merge sort or quick sort because it wouldn't be merge sort or quick sort because you would have to perform n log n comparisons based on the number of keys, and that's technically has higher potential for a faster runtime. For a slower runtime, sorry. So the length of all ASCII characters is really large. It's 255, like Noah said, I think. But I guess if you could argue that if you're sorting on really, really long strings, so they're all like 1,000 character long strings, and then you're sorting those using counting sort or arraydic sort, it could be bad because then you're arraydic sort, it could be bad, but because then you'd have to create this big space for all the possible elements. But we're kind of just trying to look at like if it was just a few characters, then like the point is that counting sort has the potential to be faster than comparison sort. At one point, are there too many keys for counting sort to be slower than merge or quick sort? To be honest, I'm not sure if there's like an exact value that we're looking for. It kind of just varies based on the alphabet. Just to clarify, alphabets and counting sorts are any group of elements that we can use as keys in sorting things. Yeah, so like digits 0 to 9, characters A to Z, something like that. ASCII 0 to 225, 255. Yeah, so I guess the question that we should answer is like, in what cases would you pick counting sort over comparison sorts? So if we're just sorting like numbers, like let's say we know that all our numbers are from 0 to 9, then we have a pretty small alphabet, and we can just count them and put them in the space where they're supposed to be. That would be pretty quick as opposed to comparison sort, which would take n log n time versus the n time for that counting sort. So it's all situational. It really depends on what you're working with. I feel like for this question, because we didn't add a lot of specificity as to like, what's the maximum length of the string or something like that, it's hard to say whether a radix sort would make sense or a comparison sort. And I'm sure on an exam, we would give more information, so it's less unclear. Are radix sorts stable? There's no, so yeah, they're not stable because you're not even like swapping the elements into their old places, and you're like creating new elements almost entirely because you just count the number of ones, the twos and the threes and stuff like that. But stability doesn't matter as much for radix sort in the sense that you can't use radix sort to sort like objects or something like that. You're sorting things that will have like some kind of primitive value in an alphabet. So like you don't necessarily need stability. Yeah. Counting sort is stable. Let me double check. Okay, yeah, I think they can be stable, but you would have to use extra space to keep track of like the order in which they were originally placed to make sure that they're maintained in the same order.
Radix sorts are usually stable in their implementation.
Yeah, sorry for any confusion there.
Okay, so I believe this is the end of our presentation. So are there any more questions relating to sorting or any of the stuff we discussed today? If not, then it was lovely to see you all. Oh, just to double check. So counting sort, LSD and MSD are all stable, right? And the answer is yes. At least the way it's, okay, so why is stability important? Okay, so imagine you have a roster full of fourth graders, right? And you're at a school and there's multiple classrooms, right? So there's like 5 different classrooms with different teachers and there's fourth graders scattered throughout them. So what you want is for whatever you're doing, you want a list of all the fourth graders by, from each classroom alphabetically. So the first thing you do is you sort by their names. So you get the alphabetical list and then you sort by classroom. And since the sort you're using is stable, the sort will be, you will have like blocks for based off of what classroom the students are from. And then within each block, all the student names will be alphabetical. So that's why stability is important for situations like this. It comes up a lot in database stuff. If you're interested in those type of situations, I think they might go over, in some regard, this kind of stuff in 186. So that's why stability is important. I see the question about will we be asked to implement sorts on the final or just do problems about them. I cannot really confirm or deny what type of problems there will be on the final. I myself have not seen it. That's handled by other people who are in 61B core staff. So all I can say is that it has happened before that you've had to implement sorts, and it has happened before that you had to do problems about them. So just to be safe, I would study both. Yeah, and if you're interested in the stability thing, I think there is an example from lecture that kind of has the visuals to go along with what I just said. Yeah, any other questions? Slide 130. Which slide is that? So according to, let me open up the slides. Slide 130 is, yeah, okay, yeah, we'll fix those. Are we gonna go over an exam level problem? This is more of a conceptual review type of thing. If you're interested in exam level problems, we did have a review session on the comparison sorts, which you can look for that worksheet. You can also look at the discussion sections. There's an exam prep discussion section for both comparison sorts and counting sorts that has exam level problems. Other than that, the best thing to do is look at previous exams and their walkthroughs, but we will not be going over any exam level problems now. When would we use merge sort or quick sort? Like we said, quick sort has a habit of sometimes not going so well, right? So a lot of programs use merge sort instead to maintain that sort of, like, have it not stability in the way we were talking about before, but like a stable runtime where we know it's going to be n log n no matter what. It kind of depends on what programming, what you're doing and what language you're using and stuff, which one will be used.
I also got a question in the chat. Can all the sorts mentioned be in place? The ones that can be in place are selection, insertion, heap, and quick. Counting sort and merge sort cannot be. There is an in-place implementation for merge sort, but it's pretty complicated, and I think we focus on the not in place one.
Because of the whole zip array mechanism, the in-place version of merge sort is way past this class. And I believe for radix sort, we don't do it in place. It's physically possible to do it in place, we just don't. Okay, great. If you guys have any more questions about sorting, please ask on Ed. I think there is some problems on slide 130, but we will fix that. Repeat what one more time? Okay, everything we covered in this thing is in scope. What is not in scope is in place merge sort, which you guys don't know. We never covered it at all in this class because it's very complicated. And I believe LSD and MSD, we will assume that it is not in place, but read the test carefully because sometimes we will say the sort is in place when it normally isn't or something to make you guys think a little bit harder. But everything we covered today is in scope for sure. And a little bit that we didn't cover, such as 3scan, it is in scope, we just didn't cover it for time reasons. So for heap sort, if you're confused about full heapify versus remove max, that's more of a heap question versus a sorting question. So I think that your best bet would actually be to go back and look at the heap lectures, because heapification, the idea is your entire heap is completely screwed up. So you're gonna have to do what we call bottom-up heapification, where you start with like the bottom row and you go up, up, up. heapifying each node as you get there and the tree below it. And then remove max, obviously just pop the top node off. The rest of the tree is already in nice heapified form. So in that case, returning the heap property is a lot faster. But if you're confused about that, that's a heap problem, not a heap sort problem. So I think we covered that in the heap lectures and possibly also the heap sort lectures. Anything else? Last minute questions? Of course, we'll also be active on Ed for the entirety of this week. There will be plenty of opportunities to ask more questions. Yeah, so if you're wondering when insertion sort is faster than quicksort, the answer is it's in a very, very specific scenario. Insertion sort is faster than quicksort when there's two things happening. The first is when there's less than 15 items. And this is just because the way the math works out, if there's 15 items or less, insertion sort is always faster than any other sort. The other option is when there are things called inversions. So an inversion is when like an item that should be after a different item is before it instead, right? And so insertion sort is very fast when there are very, very few inversions. And the reason is because in insertion sort, if most items are already in the right spot, you only have to compare most of the items to their immediate left neighbor and be like, we're all good, no need to move. And then you don't have to move anything around. So when there's very few inversions, insertion sort is great because quicksort requires you to still look at all of the elements because it doesn't have any sort of like get out faster path when things are already mostly sorted. Only insertion sort really has that. Anything else? Great. Okay, so we are going to end it here for today. This will be posted on YouTube if you want to come back to it. But other than that, I hope you guys have a great week and feel prepared for the exam. Good luck, everybody. And see you guys all hopefully at the final.